So, what is everything made of? It's one of the oldest questions we've ever asked. And the answer, the atom, well, its story is less like a boring science lesson and more like a fantastic detective mystery, just packed with clues, red herrings, and some absolutely shocking twists. Okay, let's get right into it. For the longest time, the answer seemed pretty simple. Way back, ancient Greek philosophers like Democritus imagined this thing called an atomio, literally an uncuttable particle. Over in India, Acharya Kanada talked about the paramanu, this eternal, indivisible speck of matter. This basic idea that everything boils down to a tiny solid ball stuck around for centuries. It was finally put on a real, scientific footing in 1808 by John Dalton, who basically said, yep, it's the ultimate building block. But right away, there was this nagging problem with the simple, solid ball model. I mean, think about static electricity. You rub a glass rod with silk, and suddenly they're charged. A totally solid, neutral ball just can't do that. That little spark of static was the very first clue that the atom wasn't so simple. There had to be smaller, charged pieces hiding inside. Okay, so the first major break in the case came with the discovery of a tiny, negatively charged particle, the electron. This was great. It totally explains static electricity, but it immediately opened up a brand new mystery. If atoms have these negative little bits inside, but we know they're neutral overall, where's all the positive charge to balance things out? J.J. Thomson came up with the first real proposal in 1898. He pictured the atom as something like a plum pudding. You've got this ball of spread out positive goo, and then the negative electrons are just kind of scattered throughout like plums. And honestly, this was a huge step. For the first time, we had a model that actually included the electron and explained why atoms are neutral. It really seemed like a perfect fit. So to test this whole pudding idea, a physicist named Ernest Rutherford set up a pretty clever experiment. The plan was to shoot these tiny particles through a super thin sheet of gold foil. Now, if the atom really was just a soft pudding, those particles should have sailed right on through. He was just expecting to confirm Thomson's idea. What he found instead, well, it was about to change physics forever. The setup itself was really straightforward. You have a source that fires off positively charged alpha particles. Think of them like microscopic bullets. You aim them at this incredibly thin sheet of gold foil, just a few thousand atoms thick. And then you surround the whole thing with a screen that flashes whenever a particle hits it. Simple enough, right? But the results, they were just unbelievable. Yeah, most of the particles went straight through like he thought, and some were deflected a little bit. But, and this is the crazy part, a few of them, a tiny, tiny fraction, bounced almost straight back. Rutherford's quote here just perfectly captures the absolute shock. It was completely impossible if the plum pudding model was right. We're talking about only 1 in 20,000 of these alpha particles bouncing back. It's a tiny number, but it meant everything. It meant there had to be something incredibly small, incredibly dense, and positively charged deep inside that atom to cause a ricochet that violent. The soft pudding model was completely, utterly dead. That one shocking result just blew the old model out of the water. Rutherford had to go all the way back to the drawing board and basically invent a new picture of the atom from scratch, one that could actually explain what his experiment was showing him. So in 1911, Rutherford came out with this radical new idea. The atom wasn't a pudding at all. It was more like a miniature solar system. Almost all of its mass and all of its positive charge were crammed into an impossibly tiny center he called the nucleus. And the rest of the atom? It was almost entirely empty space, with these little electrons orbiting the nucleus, kind of like planets orbiting the sun. And you know what? This nuclear model explained the gold foil experiment perfectly. But in solving one mystery, it accidentally created a brand new one. And this one was, frankly, even more catastrophic. See, according to every law of physics they knew at the time, this new atom couldn't possibly exist for more than a tiny fraction of a second. This was the crisis, the absolute core of the problem. If the atom really is a tiny solar system, why doesn't it just immediately destroy itself? Physics had a very clear answer for what should happen, and it was completely, totally wrong. Okay, so here's where everything just fell apart. The laws of physics back then were crystal clear. Any charged particle that changes direction, like an electron in orbit, is accelerating. And any accelerating charge is supposed to radiate energy away. That means every single electron should lose power and spiral into the nucleus in a death spiral in less than a billionth of a second. But Obviously, atoms are stable. We exist. Everything exists. Classical physics was fundamentally broken when it came to the atom. So the puzzle was clear. Rutherford's model had to be right, but all the physics of the day said it was impossible. It took this brilliant young Danish physicist, Niels Bohr, to propose a solution so radical that it meant basically throwing out the old rulebook entirely. Bohr pretty much just said, hey, what if the normal rules just don't apply down here at the atomic scale? He made 3 incredibly bold claims. First, electrons can only exist in special fixed orbits, kind of like designated lanes on a highway. You can be in this lane or you can be in that lane, but you can never be in between. Second, while they're in one of these special orbits, they're somehow magically exempt from the laws of physics. They don't radiate energy, they don't spiral in. And third, they can junk between these orbits, but only by absorbing or spitting out a very specific chunk or quantum of energy. And the thing is, Bohr had some powerful evidence to back up these bizarre new rules. For decades, scientists had known that if you heat up hydrogen gas, it doesn't just glow with a continuous rainbow. It only gives off light at very specific, sharp lines of color. And Bohr's model explained this perfectly. Each one of those lines corresponded to an electron leaping from a higher orbit down to a lower one, releasing a single photon with a very specific energy, which means a very specific color. It was beautiful. Bohr's model was a gigantic leap forward, no question. But it wasn't the whole story. It felt more like a patch on the old physics, not a completely new theory. It worked flawlessly for hydrogen, which only has 1 electron, but it completely failed for more complex atoms. And most importantly, it didn't explain why. Why were only certain orbits allowed? The final, deepest piece of the puzzle was still missing. The final revolution, the last big step, required thinking about the electron in a completely new and, frankly, bizarre way. This last move would take us out of the world of planets and orbits and into the strange, probabilistic world of quantum mechanics. The big idea, the final clue, came from Louis de Broglie in 1924. He suggested that, hey, maybe the electron isn't just a tiny ball. Maybe, like light, it also behaves like a wave. Think about a guitar string, right? It can only vibrate in ways that create specific notes because the wave has to fit perfectly along the length of the string. De Broglie said an electron's orbit was just like that. Only orbits where the electron's wave could fit perfectly around the nucleus without canceling itself out were allowed. This was the first real explanation for why Bohr's orbits were quantized. And then Werner Heisenberg came along and delivered the final nail in the coffin for the idea of a simple orbit. His famous uncertainty principle proved that there is a fundamental limit to what we can even know about a particle. The more precisely you try to measure an electron's location, the less you know about where it's going, and vice versa. It means you can literally never, ever know an electron's exact path, because a thing like a path doesn't even really exist for it. The very idea of a neat, clean orbit had to be thrown out for good. So all of this leads us to where we are today. We have to completely abandon the idea of an orbit, that clean, predictable path, and we replace it with this new idea of an orbital. Now, an orbital isn't a path. It's a 3-dimensional map of probabilities. It's a cloud that just shows where the electron is most likely to be found at any given moment. It's not that the electron is zipping around inside the cloud. In a very real sense, the electron is the cloud. And that brings us to our modern picture of the atom. It's this fuzzy, ghostly, wonderfully weird place that operates on a set of rules completely alien to our everyday world. So think about that journey. We went from a solid, uncuttable ball to a plum pudding to a miniature solar system, and finally to this bizarre, ghostly cloud of probability. All of that in just over 100 years. It really makes you wonder, as our tools get sharper and our ideas get even bolder, what new picture of the atom is waiting for us in the next 100 years?